So this lecture will be a segue of sorts into part 3 of the course. We will still talk a little bit about price of anarchy style guarantees for the end of lecture today, but we're really going to shift our focus now to the question. We've been talking about equilibria for 7 weeks. Where do these equilibria come from? Do they grow on trees? How do players find them? Okay. So can players reach an equilibrium? For starters, even just in principle, even just forgetting about computation and how do they coordinate and so on, how would they find an equilibrium? This has been studied a little bit in economics, but not, in my opinion, enough. But as computer scientists, we really want more than this. Players should reach an equilibrium not just eventually, but in our lifetimes, okay? Quickly, polynomial time. And this is something that really, unsurprisingly, maybe was not studied at all pretty much until computer scientists took up the issue. And we'll see in week 10 that there are actually some complexity theoretic barriers in general to computing equilibria quickly, not just decentralized by players, but even by centralized computation. But in the happy cases where you can compute equilibria quickly, at least in principle, then the question is, how does this actually happen? So what are the learning algorithms or learning procedures by which players might plausibly reach an equilibrium in a game that they're trying to figure out how to play? Okay. So why do we care about these kind of questions? Well, we've been, like I said, reasoning about all of these systems, auctions, networks, and so on. We've been reasoning about their equilibria. Okay? And essentially, we're sort of assuming that that's the operating point of these systems and drawing conclusions from it. So, giving a constructive argument about why these systems are going to be at equilibrium, that justifies all of this equilibrium analysis. In particular, just as one example, the last couple of weeks we've been talking about efficiency properties at equilibrium, so this is going to justify the price of anarchy analyses we've been doing for the last couple of weeks. But if you're reasoning about some other properties of equilibria, maybe not their objective function value, but something else, again, these questions are what justify focusing on just the equilibria. Now, to reason about these questions, do players reach an equilibrium? If you think about it, we fundamentally need a model, then, for how players behave when they're not at an equilibrium. Right, so far, pretty much all we've assumed is that an equilibrium persists. If players reach there, they'll stay there. And sort of intuitively, if you're not at an equilibrium, it shouldn't persist. Something else will happen. So the question is, what else is going to happen? And we need to pin that down to start making formal statements. So when people talk about learning dynamics, this is really what they mean. They're sort of positing some way by which player behavior evolves over time. And so to be clear, our goal will not be so ambitious as to posit some model that seems to literally describe how people might actually learn in a game. Okay, that's ambitious. Kind of any specific model is going to probably seem not fully convincing. So rather, what we're going to strive for is simple and natural models that give us predictions, that tell us about whether we'll have convergence or not, what things will converge to, how quickly, and so on. And then ideally, we'd like to draw the same conclusions from multiple different learning processes, multiple different dynamics. So if we can have different models that all lead us to the same conclusion, that lends plausibility and confidence to the conclusion that these models are predicting. Okay? So that's what we'll be looking at, simplistic learning dynamics that we can reason about with an eye toward, hopefully, kind of replicatable results across different choices of the dynamics. We'll talk about mostly 2 different styles of dynamics in this class. Today is going to be devoted to best response dynamics. Okay. The idea is very simple. This is just a process, an iterative process by which players might strive for a pure strategy Nash equilibrium. Okay? So at all times in this process, players will be playing pure strategies. The other dynamics we'll look at, that will not be true. Okay? But for today, all pure strategies. So if you're at an outcome, so here's our model of what players do out of equilibrium. So while an outcome is not a pure strategy in Nash equilibrium, that means there's some player with a beneficial unilateral deviation. So we pick one of them. For now, it's arbitrary. And we just let them pick a beneficial deviation. Again, for now, arbitrary which one they choose. Okay? So before the player was playing its strategy SI, its cost decreases or its payoff increases if it switches to SI prime, and we just let it switch. We keep S minus I fixed. Okay, so in each iteration, exactly one player will update their strategy. The other K minus 1 players will stay fixed. Okay? So this is underdetermined, right? I'm leaving which player you choose if there are many. Underdetermined, I'm also leaving which deviation, improving deviation to choose, if any, underdetermined. We'll specialize those only as needed through the lecture. So if this process converges, if it halts, what kind of outcome is it going to halt at? I mean, we just look at the stopping criterion, right? So the only way this thing will halt is if it finds a pure Nash equilibrium. And conversely, if it finds one, it will halt. Okay? So note, if, that's of course a big if, best response converges, it is to a pure strategy Nash equilibrium. So the contrapositive then says in a game with no pure Nash equilibrium, of course, best response dynamics will not converge, it will cycle. As you'll see on the exercise set, best response dynamics might even converge in the presence of a pure Nash equilibrium. Okay, just because there isn't one doesn't mean that this procedure is automatically going to find it from an arbitrary starting point. Okay? But where best response dynamics do really well is in potential games, which includes almost all of the applications we've been studying for the last few weeks. So recall a potential game. So we discussed potential functions. We used them a couple different times on Monday, and we introduced them last week to prove existence of pure equilibria in routing games originally. So in general, it's a game that admits a potential function, which I've been calling phi, with the property that it tracks the deviations by all players simultaneously. So meaning, for all starting states S, for all players I, for all deviations, beneficial or otherwise, that I might take, the change in phi is exactly equal to the change in cost incurred by that player, that deviating player. Okay. So if player number 7 deviates from some outcome and its cost drops by 10, the potential function value also drops by precisely 10. Okay. We've seen a number of examples. So the first one was atomic selfish routing games. Then there were location games. Those were also potential games, where the surplus was the potential function. And just last lecture, we introduced network cost-sharing games, which are also potential games, okay, with the Rosenthal potential. All right. So most of the examples from the last couple of weeks fall into this class. We've mentioned a couple times that potential games always have pure strategy Nash equilibria. The outcome that's the global minimizer, the potential function phi, has to be a Nash equilibrium. All deviations only make the potential bigger, so they only make the deviators bigger. That's a Nash equilibrium. But if you think about it, even more is true. There's a rather more constructive proof that every potential game has a pure Nash equilibrium. Namely, pick any starting state you want, let best response dynamics run, it's going to stop at pure Nash equilibrium. Okay. So this was really articulated by Maunder and Shapley. So in a potential game, it should be finite, like the ones we've been talking about. Best response dynamics converges to a pure Nash equilibrium. The proof is one line. What's the proof? Why does best response dynamics have to halt in a finite potential game? Yep. Right, that's the key point. In every iteration, some player moves, they switch to it's a beneficial deviation, so their cost drops. By the defining property of a potential function, if the cost drops, the potential drops. Okay? So you can't cycle. Right? It's strictly decreasing every time. It's a finite game, so you run out of outcomes. Got to stop. Okay. Good. So that's cool. So remember, we were saying, thinking about equilibria, can players reach equilibrium? So this is basically a yes to the first question in principle. Sure, they just follow best response dynamics. If you're in a potential game, you will converge. How about the second question? How about quickly? So what can we say about the speed of convergence? Okay. Well, it sort of depends how strongly we want to define what it means to converge. Okay? So we're going to talk about sort of three different notions of what it means to converge. The first one only briefly. The first one's the strongest, which is you get to a pure Nash equilibrium. It's sort of the obvious definition. That need not be fast. We'll understand that more, why it has to be slow, in the last week of the class when we talk about the complexity of these problems. So, you could make some strong extra assumptions. So like if you assumed that this potential function phi was integral, and if you assumed it was polynomially bounded, then you'd be fine, right? Because then every iteration, if the potential drops, it has to drop by at least one because it's integral. If it's polynomially bounded and non-negative, then you run out of potential in a polynomial number of iterations. And there are examples which satisfy those hypotheses. But in general, if the potential function is not polynomially bounded, it can take an exponential number of iterations to reach a pure equilibrium. So that's all I'm going to say about that strongest notion of convergence. Okay? But we'll revisit it in a couple of lectures. So the other two notions I'm going to talk the rest of the lecture about. So I'll talk about both of them at length. So the next idea, to the first of the two main approaches we'll discuss, would be, okay, maybe it's not important we get to an exact Nash equilibrium. As long as we're at almost a Nash equilibrium, that's good enough. Okay. So, can we reach an approximate pure strategy Nash equilibrium and a polynomial number of iterations? Okay. And that would be a pretty good positive result if we could do that. By an approximate pure Nash equilibrium, we mentioned this briefly last week. This just means that you might have a deviation that could decrease your cost, but not by very much. Okay, so in this lecture, we'll use the definition. At an epsilon Nash equilibrium, you can only go down by you can only get multiplied by a 1 over 1 minus epsilon factor. Okay? So you might want to think of epsilon as like 0.1, something like that. That would say that any deviation, your cost is going to be at least 90% of what it is now. Okay, so that would be a 0.1 approximate pure Nash equilibrium. Now, one reason, so intuitively, it seems like being at an almost Nash equilibrium should be basically as good as being in a Nash equilibrium. And I even asked you on the exercise set to work out sort of a formalization of that idea, which is at least if you're in a smooth game, you just proved that epsilon pure Nash equilibria have price of anarchy almost as good as exact pure Nash equilibria. Okay, so if you care about the price of anarchy and it's a smooth game like all of the examples we've seen, then you really don't care if it's an epsilon Nash or a real Nash. Okay? So we'd be pretty happy with this result. Good. So we're also, out of respect to the epsilon, going to change the dynamics a little bit in the obvious way. And this is really the key to the speed up. Okay, so I'm going to show you a positive result for epsilon pure Nash equilibria, which does not hold for exact Nash equilibria. And the reason is that we can insist in best response dynamics on deviations that actually help the player, not just a tiny bit, okay, it doesn't just save you a penny, but that helps you a lot. And we're only going to focus on deviations that offer a significant improvement. So that's epsilon in best response dynamics. So while there exists a player, that can decrease its own cost by at least 1 minus epsilon factor. So again, if epsilon was 0.1, this would say if you can cut your cost to 90% of what it is now, then you're eligible. So I'll call this an epsilon move. If it multiplies your cost by 1 minus epsilon or less. So while there's a player that has an epsilon move, let one such player take an arbitrary such move. Okay? Yeah. Yeah, right. So can so let's say with deviation such that new cost is at most 1 minus epsilon old cost. Sound good? Thanks. So I'm still leaving underdetermined if. So if there are many players that have an epsilon move, you pick one of them arbitrarily. If the player has multiple epsilon moves, any one of them. I don't care. The thing you're not allowed to do is take improving moves that improve only a tiny bit. Okay? And that's key to the speed up. All right. So this thing, and epsilon best response dynamics fits naturally with epsilon pure Nash equilibria, because if this thing converges, the stopping criterion is nobody has an epsilon move, so nobody can multiply their cost by 1 minus epsilon or less by deviation. Okay, so that's our definition of an approximate Nash equilibrium for today. So if it converges to an epsilon move. And if it's in a potential game, and that's all we'll be talking about today is potential games, again, every one of these decreases the potential, so there can't be an infinite number of these. Okay? We're even hoping there's only a polynomial number of these, but it's clear there's only a finite number of these. So it converges to an epsilon, pure Nash equilibrium, and a potential game. So finite convergence is clear. And what's interesting to think about, and which we'll be talking about for the next half hour or so, is how fast. Are there interesting conditions under which we can get a polynomial time guarantee on the number of iterations of epsilon best response dynamics before we converge necessarily to an approximate pure Nash equilibrium? Any questions about the setup? So we're going to spend a lot of the lecture on the following theorem by Shannon-Sinclair, 2007. So what Shannon-Sinclair do is they identify some conditions on a routing game that are sufficient for a polynomial time guarantee for epsilon best response dynamics. Okay? So they're not going to prove it for every single routing game, and it's not going to be true for every single routing game, but they identify a nice class where you can get this really quite strong result, that you get convergence in polynomial time to one of these almost equilibria. So here's what they say. So consider an atomic selfish routing game. It need not have affine cost functions, but if you want to have that case in your mind, that's perfectly fine. So let me tell you what the assumptions are. So here's the biggest one. The biggest one is the assumption it's going to be a symmetric game. That is, every player has exactly the same source, and exactly the same sink. So in particular, every player has exactly the same set of strategies, okay, the ST paths. Other than that, the network topology can be arbitrary, be an arbitrary network, so that's good. So here's a non-trivial assumption, but it's less severe. We're going to call this the alpha-bounded jump condition. Sort of a Lipschitz condition on the cost functions, which just says when you add one new player to an edge, the cost doesn't totally blow up like crazy, okay, by at most an alpha factor. So for all edges, for all possible load amounts x, the cost of an edge with one new player, well, so we're in the routing context. We're only talking about routing games, so these are non-decreasing. We're back in that world. So the cost only goes up, and it goes up by at most an alpha factor. Okay? So that's the alpha-bounded jump condition. And most cost functions you care about are going to satisfy this with some at least semi-reasonable value of alpha. The one thing that it excludes, which you really do want to exclude for these kinds of results, is that you can't be 0 and then suddenly jump to something positive. Okay? So that would violate this for any finite alpha. Okay? So you want to think about cost functions that are positive already with one player. But that's a reasonably weak assumption. Okay. So 3, as I've sort of discussed, we're only going to be talking about epsilon best response dynamics, not best response dynamics. It's important that we disallow minuscule improvements to get the fast convergence bound. And 4 is not essential, but I just have to precisely specify some dynamics. There's a lot of choices I could make, and this theorem would be true. The choice I'm going to make, I'm only going to prove one version of the theorem, is the way I'm going to pick a player in an iteration when there are many players that have an epsilon move. Again, remember, in epsilon best response dynamics, we identify the players that have an epsilon move, a way to improve their cost by a lot. And then over here, we just pick an arbitrary one to move. For the proof I'm going to give you, I'm not going to pick an arbitrary one. I'm going to look at all the players that have an epsilon move, and of them, I'm going to pick the one who has the most to gain, who in an absolute sense, its cost would drop the most. Okay? So if one person has an epsilon move that drops by 100, and a different one is 200, I pick the one with 200. Okay? So it's an absolute drop, not relative drop, absolute drop. Okay? So max gain dynamics. So player with the biggest absolute improvement moves. And moreover, I ask that that player indeed chooses the strategy that realizes that maximum possible decrease. Okay? So the player with the biggest drop will pick its best response. All right? All right, so so these are the assumptions. So what do you get? Well, you get polytime convergence. So that's nice. Okay? So then, converges in, so what is polynomial time? Well, it's linear in the number of players k. It's linear in this Lipschitz condition alpha. It depends linearly on 1 over epsilon. So epsilon again is like this 0.1. That's how close to equilibrium we want to be. And then it's logarithmic in the potential function value. Okay? So this will become more clear as we do the proof, but routing games have a potential function. I'll write it back on the board if you've forgotten the form, that's fine. We have to seed best response dynamics. We have some starting point. So S naught is the place where you're going to start the dynamics. That has some potential function value. The potential has some minimum possible value. That's the denominator. Okay? So it's log in the ratio of this, which is polynomial in the input size. Okay? So that's the guarantee we're going to get for selfish routing games, single source, single sink, alpha bounded jump condition for the max gain dynamics. So something which I want you to know, but it's far from obvious, is that if you relax the assumptions 1 through 3, then this theorem becomes false. Okay, so the first 3 assumptions are really important for polytime convergence. Multiple sources, multiple sinks, you don't have it. If you throw out the alpha-bounded jump condition, you don't have it. And if you don't disallow tiny improvements, you don't have it. Okay, so you really need 1 through 3. Well, you'll see them in the proof, but the theorem's actually false without them. 4, a zillion variants still work. Okay, so this conclusion is very robust to varying how you implement epsilon best response dynamics. And that's a good property. Okay, because again, we don't really literally believe in any of these instantiations of epsilon best response dynamics. So we're really looking for conclusions that hold for lots of different instantiations. And you get that here. Really all they need is sort of a minimal no starvation condition. On the exercise set, I'm going to ask you to kind of reprove the theorem for one variation, where instead of the biggest absolute gain, you pick the player that gets the biggest relative gain in each iteration. Okay? So that's what we're going to prove. Is the statement clear? Yep.
I just want to make sure I understand the alpha-bounded jump condition.
Yep.
Would that not allow x squared as a cost function? Because then if you have enough players, you'll multiply by more than alpha if you add another player? That is the cost of 0.
No, but this is only for every x at least 1. Polynomials are fine, actually, right? So like imagine you go from 4 to 5. Right, and you're squaring, right?
When you from 1 million to 1,000,001, wouldn't that raise your cost by a lot?
Well, but remember that's alpha times your original cost. So no, alpha's going to be like 2 per square, or 2 to the 2 or something, right? Alpha times, let me think about this. Yeah, right? Just do the expansion, right? Take x plus 1 squared, x squared plus 2x plus 1. It used to be x squared, so you're fine.
Yes, that's fine.
Yeah. So polynomials are fine here. And we're not, and for those we don't care about 0 either because we only need it for x at least 1. Obviously, the cost functions are essentially undefined at 0. So, other questions? Yeah.
You said that this converges in finite time. Why is that obvious?
In a finite game?
Oh, in a finite.
Yeah. Other questions? All right. So let me tell you the plan. The plan is 2 lemmas and then the proof of the theorem, but let me tell you something more useful than that. So essentially, all right, so what was the argument that we just converge in finite time? Well, we know that the potential goes down, okay, which precludes cycles. So the whole goal is to say, all right, well, with all these assumptions, and in particular with epsilon best response dynamics, since we're only making significantly improving deviations, shouldn't it be true that in every iteration the potential goes down by a lot? Okay, so it decreases not just by some positive amount, but significantly. And if it does, if we can prove that the potential goes down by a lot every single iteration, so say, by 1% every iteration, then it just we can't have that many iterations because we make so much progress in each iteration. So how would we prove that the potential goes, and that is what we're going to prove. We're going to prove the potential goes down by a lot every single iteration. So how would we do that? Well, what we're sort of wishing were true, so remember in epsilon best response dynamics, it means whoever deviates, their cost goes down by a lot. So the good case is where we pick a player whose cost is huge. Right? So if we pick a player whose cost was like half of the total cost and its cost went down by a lot, that would be a significant improvement. Our concern is just that we wind up picking some player with tiny cost. Okay, and therefore its high relative improvement, epsilon for it, is too small. Again, we get slow convergence. So the technical meat of this proof is just arguing that as we do epsilon best response dynamics with the max gain instantiation, we may not be picking the player with the biggest cost of them all right now, but we'll pick a player whose cost is sort of sufficiently close to the average that every single iteration will give us a big drop in the potential. Okay, so that's the plan. All right. So the 2 lemmas say the following. The first lemma, which is easy, is going to say, at every iteration, there exists a player where if that player if we picked that player to do an epsilon move, then we'd get a big decrease. Okay, so at least there's one player out there who would give us a big decrease in potential. Lemma 2 will say, well, we may not pick that player, but the player we pick is almost as good with respect to convergence. Okay. All right, so Lemma 1 is our warm-up. So in every outcome of this selfish routing game with common source and common destination, there is always a player whose cost is large. Okay? So there's some player out there. So what do we mean by large? Well, we're actually going to prove that it's at least a kth fraction of the total cost, but what's more relevant for us is that it's a kth fraction of the potential, because the potential is what we're going to use to track our progress. So phi, the potential function value of the current outcome over k. Okay? Now, what this lemma tells us is that in a given iteration, there is a player out there, namely this player I, where if this player is the one chosen to make an epsilon move, we're stoked. Okay? Why? Well, its cost is at least a kth fraction. Don't worry about this k, right? So the cost of this player is proportional to the current potential. If this person makes an epsilon move, its cost is going to drop by a lot, by like 10%. What's the definition of a potential function? It says whatever the drop in cost that a deviator experiences, that exact same amount, the potential drops. Okay, so if this person's cost drops by 10%, then the potential is also going to drop by a significant amount. Okay, so that's what this is saying. There exists a player out there, player I, whose cost is so big that if it made an epsilon move, we'd make big progress in decreasing the potential. Now, this lemma does not say that we pick this player I. That's the problem. That's why we need lemma 2. Okay? But first, let's just prove this. All right, so let's remember actually, this potential function is obviously playing a crucial role. You've seen it a couple times, but it's the whole way that we're measuring progress. So let's just remember the form of it. And actually, let's more specifically remember how it compares to the cost. Okay? So the potential, Rosenthal's potential, for all these kind of games has this form. So f sub e, as usual, is the number of players who are picking a path that contains edge e. And we evaluate the cost function at each value of I. So if there's 5 players using an edge, we look at the cost function of that edge evaluated at 1, at 2, at 3, at 4, and at 5. So I'll draw you a picture that I've drawn for you once before. So on a given edge, you can think of the potential as just basically integrating, okay, the area under a curve. Okay, so if this is sort of a cost function, then here's your potential function value. Whereas the cost in a selfish routing game is just the sum over the edges of, rather than a sum over these f sub e things, the number of players using the edge times the cost each of those players experiences on the edge. So that would be the bounding box of this curve. Okay? Recall in the routing context, we assume that cost functions are non-decreasing. Okay, so this curve is going up. So indeed, the bounding box will subsume the area under the curve. All right, so what we have is that. Okay, that's what I just argued geometrically. The cost of any outcome in a selfish routing game is lower bounded by the potential. This is the flip direction from Monday. In Monday, because the cost functions were decreasing in network cost sharing games, the potential only overestimated. Here only underestimates because cost functions are non-decreasing. So this is just the cost of S, and this is the potential function of S. Okay? So the upshot being, recall, and we'll use this a couple times today, in routing games, potential only underestimates cost. Okay? In routing games, potential only underestimates cost. So now back to lemma 1. Why is there a good player out there? A player with high cost relative to the current potential function value? Well, so remember, the cost of an outcome is just the sum of the player's costs. So the average player cost is just the total cost of S divided by K, right? That's the average cost of some player picked at random. So the player with the highest cost is at least that average. So this player I, whose own personal cost is at least as high as the average cost, which is lower bounded by the potential. Okay? So that's it. That's lemma 1. Right? So really, lemma 1 is just recalling that the potential underestimates cost for routing games. That's really what lemma 1 is. Yep.
I think there's something in the definition that you can add any constant potential function and still be a potential function.
Okay.
So it seems like it adds like a million to your potential function, and in that case, the component would fall.
Okay, but how about for this proof I don't add a million and I use this potential function?
Well, right, but I mean, it raises the question. There's some kind of a baseline. So how do you know which it is?
Well, I mean, so if you like, one thing to notice is if I added any constant to this potential function, this inequality would be false. So in some sense, this is the largest potential function that point-wise lower bounds the cost. In that sense, it's the obvious one to use if you have this proof approach in mind. Because notice that if there's exactly one player on an edge, then the two things coincide. Okay? So I can't raise the potential anymore. Okay, so lemma 2. So, all right, so this tells us that if we are so lucky as to choose player I for an epsilon movement iteration, then we're good to go. Okay, and you'll see the detailed calculations a little bit later. Okay, but that player has high cost, comparable to the potential value, so if we get a high decrease in its cost, we get a high decrease in the potential. The problem is what if we pick some other player J? Our criterion is not that we're picking the player with the highest cost. That's not how we define the epsilon best response dynamics. We define it that we're picking the one with the biggest drop. Okay, it was the most beneficial deviation available. You'd expect that to be sort of correlated with who has the highest cost, but it need not actually be the player with the highest cost, it turns out. Okay? So here's what lemma 2 says. So now, we're happily running epsilon best response dynamics, and in some given iteration, some player I gets chosen. Okay? So in some outcome S, SI is going to be what player I was using before, and then when player I makes its epsilon move, that's going to be to the other strategy S prime I. Then, for all players J, the claim is that if I look at the drop, okay, so what this left-hand side is, this is how much player I's cost decreases when it switches to its old strategy to its new strategy. Again, it's going down, and remember it's an epsilon move, so it's actually going down by a significant amount. So this is not going to be the Lemmas statement, but just sort of for comparison, this inequality is just the definition of it being an epsilon move. Okay? So you shaved your cost by at least an epsilon fraction of what it used to be. All right? So this is not the statement. Okay? This is just true for any epsilon move. So what I'm going to do here instead is I'm going to write something in terms of the other players J. Okay? We already know this. We know that the decrease is large with respect to I's cost. But again, the problem is that I might not be the player with the biggest cost. But what I'm going to say is that the decrease in I's cost is even large relative to the cost of everybody else, in particular the player with the largest cost overall. So instead of epsilon CIS, which we just know, I'm going to write at least CJS, still an epsilon, but I'm going to lose an alpha factor. Okay? So I changed the J to I changed the I to a J, so it's some other player now, and I weakened the statement. Okay, I'm not claiming an epsilon fraction, I'm claiming an epsilon over alpha fraction. Alpha, remember, is the bounded jump condition, and that's at least 1. Okay, so this is a weaker statement, but it applies to other players as well. Okay. So this lemma, the proof isn't that long, but this is where the action is. This is the only place where you really use the single source, single sink assumption, and this is the place where you use the alpha bounded jump assumption. Okay? So once we have this lemma done, we'll be pretty much home free for the theorem. Okay? All right. So proof. Fixed player J. So let me dispense with an easy case. So remember, I is who actually gets chosen in epsilon best response dynamics. By definition, that means this player had the most to gain of everybody who had an epsilon move. Okay? That's how we're choosing the player. So now there's this other player that we want to say we're doing at least as well as, with this relative improvement. So if J also had an epsilon move available to it, so if J had some strategy, S prime J, whereby it could have accomplished an epsilon decrease in its cost, well then we can conclude that I was chosen instead of J, right? Both had epsilon moves. We picked I. Okay? So I's absolute gain was bigger than J's. Okay? So that means, actually, that we have this inequality, the one we're asserting even without the alpha. Okay? So imagine, okay, so think about an epsilon move. And if J has an epsilon move, then the following is true for some deviation S prime J. If I just make all these I's J's, then it has some move by which it would realize that left-hand side. That's the definition of epsilon move, if I change all the I's to J's. Okay? Because we chose I is realizing an even higher drop in its cost. Okay? So in particular, it's at least the drop that J would have experienced had it taken its epsilon move. Okay? So for a player J that actually who was actually eligible to be chosen by epsilon best response dynamics, the lemma is, a stronger version of the lemma is true if I hide the alpha. Okay? So that's the easy case. So if J also had an epsilon move, let's call this star. Then star holds. Since I chosen over J, and again, without the alpha even. All right. So the work is just, what if it turned out that J had high cost and sort of no means by which to decrease it a lot? Okay, and therefore it wasn't eligible when we were picking our player to make an epsilon move. So this is where we use the key hypotheses in the theorem. So suppose player J has no epsilon move in the current outcome S. So what does it mean that you don't have an epsilon move? It means that no matter which deviation you take, your cost is not going to go down by very much. Your new cost is going to be at least 1 minus epsilon times your old cost. And that's going to be true no matter which deviation you try. And I'm interested in that statement for a particular deviation that J could take. And this is where I really use that there's one source and one sink. Okay? So player I, the one that actually got chosen. So it had this, awesome deviation available. Okay? It switched to S prime I, and its cost drops by a ton. So the question I want to ask is, well, why isn't this good for J? Okay, so I and J, these players have the same source, the same destination. They have the same set of available strategies. So any deviation which I wants to take, it's an option, it's a feasible option for player J as well. Okay? If they had different sources and sinks, this would be wrong. Just because I have a good path, you don't have a good path if you don't have my source and destination. Okay? But I can take I's deviation S prime I, and as a thought experiment say, well, what would happen if J tried that himself? So that's what we're going to do next. So J, remember, has no epsilon move. Nothing drives its cost below 1 minus epsilon times its current cost. In particular, S prime I does not drive its cost below 1 minus epsilon times what it is right now. So since J has no epsilon move, if it tries to copy player i's deviation, so take care here, S prime I, but S minus J. Okay? S prime I is the deviation that player I actually takes in this iteration. As a thought experiment, player J is thinking about copying it, okay, with all the other k minus 1 players staying the same. Okay? So J is playing S prime I. The other players are doing what they were doing in S. Because it has no epsilon move, this deviation in particular has cost bounded below by J's cost right now. Okay? Question?
Let's see, is this after player I is moved?
I'm sorry?
Is this after player I moved?
No. That's why it's S prime I and S minus J. So in particular, I is one of the players in minus J. Yep.
And is it the cost of J or cost of I? Yeah.
Thank you. It's cost of J. Okay. On the other hand, remember, S prime I is an epsilon improving move for I. Okay, so this was our original hypothesis. So let me write that this way. Okay. So this is, let's call this A, call this B. So now here's where I want to use the alpha bounded. So I've already used the one source, one sink hypothesis. Okay? Right, that hypothesis is just to say that this outcome makes sense. Okay, this outcome wouldn't make sense without the one source, one sink hypothesis. Let's use the bounded jump hypothesis. So note, consider the outcomes. Basically consider this outcome and this outcome. Okay? So k paths are being chosen in these two outcomes each. Right? There's k paths in one, there's k paths in the other. How many paths are in common to both of those two outcomes out of the k players? So forget about the paths being ascribed to particular players. Just look at sort of the set of paths that get chosen in each of those two outcomes. K get chosen in the first one, K get chosen in the second one. The intersection of those paths has cardinality at least what? K minus 1. That's right. Okay? S prime I is chosen in both by different players, by I in one case, by J in the other, but it's chosen once in both cases. And S minus I and S minus J have K minus 2 players in common. Okay, the players other than I and J, and they're all just fixed. So K minus 1 out of these K paths in these two outcomes are exactly the same. Okay? The only difference is one gets moved to somewhere else. So if I think about the load of an edge, like suppose there's some edge which is used by 5 players here. What are the possible numbers of players it might be used by here? 4, 5, or 6. Okay? It's going to be off by 1 at most, because we only switched one path going between the two. Okay? So the loads are almost identical in the two outcomes. So now we're right in the wheelhouse of the bounded jump hypothesis. Right? We changed the load by 1, we changed the cost by most alpha. Right? You can see where that assumption came from now. So by the bounded jump condition, so particularly the way I want to do it is I want to say that in the outcome where J switches, the costs are at most an alpha factor higher. Okay? So in both cases, I'm talking about the player that's actually taking the strategy S prime I. Okay, so these are outcomes. The loads are almost the same, up to plus minus 1. On the left-hand side, I'm thinking about J's cost, because it's the player on that outcome that's actually choosing the strategy S prime I. On the right-hand side, I'm thinking about I's cost, because it's the one who's actually choosing that exact same path, S prime I. Okay? So that's C. So A comes from the fact that J has no epsilon improving move, in particular S prime I is not one. B comes from the fact that I had an epsilon improving move, namely S prime I. C comes from the bounded jump condition and the fact that these two thought experiments involve almost identical edge loads. Okay? So now how do we put these together? Or like what can we derive? So here's what I claim A, B, and C implies. A, B, and C implies that while player I, the one that got chosen in epsilon best response dynamics, maybe it wasn't the player with the highest cost, but his cost can't be that far off. Okay? It can't be much smaller than that of J. Okay? So the assertion, which is going to fall from A, B, and C when we stare at it long enough, is that J's cost in the original outcome S is at most alpha times the chosen player's I cost in the original outcome S. Okay. So why is that true? So we want an upper bound on J's cost in S, right? So imagine we start from here, okay? We start from the fact that we know that I has this epsilon improving move S prime I, okay? And so the right-hand side is at least the left-hand side. And so the worst case for the proof is when these are equal. So even go ahead and think of this as an equal sign for the moment. Okay? And so now imagine I change both the left-hand side and the right-hand side at the same time. Here I switch to J's cost if it's the one instead, using that deviation S prime I. And here I switch to J's cost in its original outcome. So if they start equal, what C says is that the left-hand side goes up potentially, but by at most an alpha factor. Okay, so we start with two numbers that are equal. The left-hand side gets bigger, but by at most an alpha factor. And inequality A asserts that the right-hand side, let's see, do I have this right? Most an alpha factor, and that has to be bigger. Yes, good. So this goes up from its original value by at most alpha, and this has to wind up smaller than whatever this became. Okay, so I started with two numbers, they're both 100. Maybe alpha's 5, then that says this is at most 500, which means this side, being less than this, has to have gone up by at most alpha and most 5. Okay? So if this is 100, that's at most 500, that's at most 500. The factor difference is at most alpha. Okay? So that's the way to think about it. Think about this starting equal. We have an upper bound on how much this side could go up, and this has to be the bigger side. So that same upper bound on how much this goes up, upper bound's how much this side could go up. Okay? So that's why A, B, and C implies that while the chosen player I's cost may not be the biggest, it's off by only an alpha factor. Okay? So now we just put this together with B, and we get that so because this was an epsilon move for I, we know this was at least an epsilon, the decrease was at least an epsilon fraction of I's original cost. J could have had cost in alpha factor. So if we want to actually have a bound in terms of J's cost, then we have to lose the alpha. Okay? And that was as claimed. Okay? And again, all of this work and where the alpha comes from just says, if we had a coincidence between the chosen player I, okay, the one with the max gain epsilon improving move, and the player with the biggest cost of everybody, we'd be good to go, and we wouldn't need the alpha. And the problem is those two criteria can choose different players. There might be one player I who gets picked because it has the max gain, a different player J with a max cost, but there can only be a difference of alpha between their costs. So that was the point. All right, so we're almost home free. Questions or ready for the proof of the theorem? I should remind you what the theorem is. So we're trying to prove that this epsilon best response dynamics converges in at most this many iterations. Linear in the number of players, the jump bound alpha, 1 over epsilon, where epsilon is the approximation, and logarithm of the potential ratio. Okay? So this will follow quickly from lemmas 1 and 2. And remember, the plan all along was to argue that every single iteration of epsilon best response dynamics decreases the potential by a lot. As long as that's true, it's sort of clear it just can't happen that many iterations. Okay? So let's see why that really is true. So in an iteration where some player I moves, so again, say from I to its epsilon improving move S prime I. So remember, we're tracking our progress via how rapidly the potential function decreases. So let's bound from below how quickly it's going to decrease in this iteration. Well, what's the whole point of a potential function? The whole point is that it tracks the change in the cost by the deviating player. So by definition, because this is a potential function, when player I deviates from S to Si prime, the change in the potential is exactly player I's drop in cost. Okay, that's what it means to be a potential function. Now, what do we know about this? Well, like we knew from the get-go, just by being an epsilon improving move, that we had this statement with an I. Okay, that's what it means to be an epsilon improving move. But we did all this work in lemma 2 to kind of say, well, figure out I's cost. Show me your favorite player J. We're even decreasing by an epsilon over alpha fraction of that player J's cost. So I'm going to use lemma 2 to lower bound how much player I's cost goes down by epsilon over alpha. And because this holds for every single player J, I may as well take the largest of all of those lower bounds. Okay. So this is lemma 2 right here. Do I still have lemma 1? No. Okay. Lemma 1, that was the easy lemma. That was really just because the potential underestimates the cost. So lemma 1 just said, look, there's some player out there whose current cost is at least a kth fraction of the overall, just by averaging. And that's going to be lower bounded furthermore by a kth fraction of the potential. So we're going to use lemma 1 now to say that there exists a player whose cost is big. Okay, so notice we're taking the largest cost over any player. And so again, this is at least a kth fraction of the average cost, which is at least a kth fraction of the potential. Okay. So that's lemma 1. So this is great. What this says is that every single iteration that we run epsilon best response dynamics, we're getting a relative decrease in the current potential function value. Okay? So in particular, let's think about, after L iterations of epsilon best response dynamics. So every time we do an iteration, we hammer the potential function value by a factor 1 minus epsilon over alpha k. Okay? So phi current, let's say, well, we started with some initial outcome S naught. Every iteration, we get an epsilon, 1 minus epsilon over alpha k factor multiplied by it. And that just keeps happening over and over again. Okay, so every iteration, gets multiplied by 1 minus epsilon over alpha to the k. Okay? So one way to think about this, right, so this means that every k alpha over epsilon iterations, it gets knocked down by a constant factor, something like 2. Okay. So if we just add a log of the ratio between the initial potential function value and the smallest potential value you could ever see, it's got a halt. Okay? So the fact that it's decreasing so rapidly means that it halts within L k alpha over epsilon. And so every this many iterations, it gets divided by a constant factor. And so that can only happen log of the ratio of the initial value and the smallest possible final value. And that's the proof. Okay? Questions? So this is great. Okay, this really kind of says, whatever it was you cared about, equilibria, it's meaningful. Right? So whether it was the price of anarchy or whether it was some other property of equilibria, or really, epsilon approximate equilibria, then it makes sense in these models. Selfish routing games, one source, one sink, bounded jump conditions. Okay? If you believe in the best response dynamics story. Okay? All right, so that's the more ambitious goal, is to really prove that dynamics make it all the way to an equilibrium, or almost all the way to an equilibrium. And because that's an ambitious goal, we needed some non-trivial hypotheses. Okay, like I said, this theorem is false, for example, even if you just look at multiple sources or multiple destinations. So there's lots of models where we've studied and proven good bounds in the price of anarchy, of pure equilibria, say, that this theorem doesn't cover, and where in fact this theorem is just false. So what I want to do now is weaken the goal, but we'll be able to get much greater reach. We'll be able to cover essentially all models that we've discussed so far in the course. Okay? So for this weaker goal, I'm going to assume that the reason you care about equilibria is because you care about the objective function value of your system. Okay? So in other words, I'm going to make the assumption that you don't care about being at equilibrium per se, and you'd be happy with a guarantee that just says, well, players might not be at an equilibrium, but wherever they are right now, the cost, so the performance of the system is as good as if they were at an equilibrium. Okay? So it's a weaker statement than saying you're at an equilibrium, or approximate equilibrium. I'm just saying the cost is as small as if you were at an equilibrium. And that turns out to hold much more generally. Okay? That turns out to hold basically for all smooth games, in the sense we talked about last week, that have a potential function. And all of the games we've talked about thus far meet both of those hypotheses. So second approach, so we're going to prove now that you reach a low-cost outcome in Pauli number of iterations. And again, by low cost, I mean as low as if you were actually at an equilibrium. You may not be at one, but the cost is just as small as if you were. Okay? And again, the two hypotheses will be smoothness, as we defined last week, and having a potential. Okay, so here's the formal statement. So this is the third application of that smoothness condition we talked about after coarse correlated equilibria and approximate pure Nash equilibria. So consider a lambda mu smooth game. And again, go ahead and think about if you want selfish routing with affine cost functions, where lambda is 5/3 and mu is 1/3, but it's a more general statement. So consider a smooth cost minimization game with a potential function phi that, like in the routing example, underestimates the cost. Okay? So if you like, think of this, as a special case. Just think about the routing games we were just talking about, but with multiple sources and destinations allowed. that'd be one case where this theorem is going to hold and the convergence theorem will not hold. Okay? So again, we're going to consider a sequence generated by best response dynamics. So an arbitrarily long sequence. It's going to be almost the same dynamics as before. So again, we're going to use the maximum gain rule, but again, it doesn't really matter much. So amongst all the players and looking at their beneficial deviations, you just pick the player of the deviation who realizes the biggest cost drop. It's actually no longer important that we only use epsilon improving moves. You can use whatever moves you want for this theorem. Okay? But again, the way we break ties amongst players who have a beneficial deviation, we pick the one with the best deviation. As usual, S star is going to be the minimum cost outcome. And the claim is for all, but it's basically the same bound here, except there's no alpha, because we're not actually making the alpha bounded jump assumption. So linear in k and whatever and epsilon, and the ratio and potential values. So for all but this many states, or time steps if you like, it will be the case that the cost of the outcome is as small as if you were at a Nash equilibrium. Okay? So cost of an outcome in the tth time step is the most lambda over 1 minus mu plus gamma times, okay, let me make this gamma actually. Is the most lambda over 1 minus mu plus gamma times cost of optimal. Okay? And what I want you to remember is there's a lambda over 1 minus mu. So when we're talking about exact equilibria, this was the bound we were getting. Okay, so like when lambda was 5/3 and mu was 1/3, we were getting a 2.5. This was our 2.5. So the interpretation here, you forget about the formula. It's just saying you're as good as if you're at a Nash equilibrium up to this gamma error factor, which you can think of, again, gamma think of as 0.1 or 0.01. As small as you like. Okay? So this is not arguing convergence. This is just saying that if you take the number of time steps long enough, significantly better than this number, then at almost all time steps, your cost will be as good as a Nash equilibrium. Okay? So there's some number of days on which no promises, cost might be big, but outside of this linear number of days, the cost is always going to be small. Okay? Theorem make sense? Okay, let me show you the proof. This proof is easier. So just to remind you briefly what smoothness is, that's this disentangling condition. Kind of says if you give me a mixed up version of two outcomes, S and S star, I can bound it above by a linear combination of the costs of the two outcomes. And lambda and mu are the coefficients in that linear combination. Okay? So proof. So consider a bad state. So here's the plan. So when we were doing our convergence result and looking at epsilon best response dynamics, our plan was to say that every single iteration, the potential dropped by a lot. Okay? We're not going to make that statement now. There might be iterations where it doesn't drop by a lot. But we're going to say that whenever you're in a bad state, one that has high cost higher than what you have at equilibrium, every bad state immediately leads to a big drop in the potential. Okay? So therefore, because you can only have so many big drops in the potential, you can only have so many bad states. So that's the goal. If you ever violate this bound on the cost, this guarantee, then you immediately get a big drop in the potential. That's going to be the proof. So call a given state ST bad if the condition fails, meaning cost of ST greater than lambda over 1 minus mu plus gamma times cost of S star. Okay? And so what we're going to prove is that the only way that the cost can exceed that of Nash equilibria is for some player to have a massive incentive to update its strategy. Okay? So you only have really bad cost when you can have a massive drop in the potential, which basically means there's some player out there that can have a big cost drop in its cost. So here's the derivation that shows that. So at the beginning, we're really just going to copy the exact same proof we used when we introduced smoothness as an upper bound technique for the price of anarchy. So let me just write out the same derivation. The cost of, so again, in our mind, originally we were thinking of S as an equilibrium, but now S is an arbitrary outcome. So the assumption in cost minimization games is that we have an upper bound in terms of the number of players. And so now remember, smoothness involves this entangled version of two outcomes. Okay, so I need to apply the hypothesis, I need to think about mixing up S and S star. S star is the optimal solution. So I'm going to write this, which is going to be true just by definition. So I'm going to think about walking up to player I and forcing it to deviate. Okay, forcing it to deviate to what I wish it was doing in the optimal solution, S star I. Now, by virtue of S being not necessarily a Nash equilibrium, but any outcome, if I force it to deviate, its cost might go up, it might go down. So I'm just going to define delta to be the change in its cost when I make it switch to S star I. Okay? So by definition, we're going to have, so again, this is making, as a thought experiment, player I switching to its strategy in the optimal solution. So now let me just write plus delta I of S, where I just define this to make the equality hold. Okay, so this is just equal to the cost drop when it switches. Okay, so this is how much I's cost drops when it switches to S star I. Could be positive, negative, or zero. If it were a Nash equilibrium, this would definitely be non-positive. Okay, you definitely wouldn't get better. Okay, but in general, this could be anything. Okay, so that's just by notation. And again, why did I do this? I did this because the sum of these terms is exactly what the smoothness hypothesis applies to. It says I can upper bound this by the linear combination of S star's cost and S's cost. So by smoothness, lambda times cost of S star plus mu times cost of S, and then I've got these delta terms hanging around. Okay? So the way to think about what I just did is I just sort of copied the lambda over 1 minus mu price of anarchy proof, but allowing for an error term. These deltas are an error term. Okay? So if this term wasn't there, we'd be done. Okay? We would just, as usual, subtract the mu term from both sides and divide, we get our bound of lambda over 1 minus mu. So this just says we're getting that bound up to this error term. Moreover, this error term has a nice meaning. Okay? This error term is just how much their cost would drop if they actually deviated. Okay, so this is somehow saying the error in the price of anarchy bound is exactly the cost you'd realize by switching to optimal strategies. Right? So in other words, the only way your cost can be big is for some player to have a strategy by which it can decrease its cost a lot. Okay, that's the whole point here. So rearranging, this is what we get. Plus 1 minus mu times the sum of the deltas. Okay, so that's just rearranging that top inequality. Now suppose S star is bad, meaning we're at one of those days, t, so that the cost in the game at this day t does not conform to our guarantee. Okay, it is not almost as good as a Nash equilibrium. The cost is higher than lambda over 1 minus mu plus gamma times the optimal cost. What this says is the only way that can happen, okay, the only way your cost in an outcome can be bigger than lambda over 1 minus mu plus gamma times the cost of the optimal solution is if this final term is at least this gamma times this cost. So this must be at least epsilon times cost of S star if ST is bad. Okay? Again, the only way that your cost can be high is because players can realize a massive drop in their cost by a suitable deviation. Okay? Well, in a bad state, if the sum of the deltas, the sum of these deviations is at least epsilon times cost S star, there exists a player whose deviation is at least the average, so that loses the factor k. So there exists I with delta I S at least epsilon over k times the cost of S star. Actually, let me remind you what delta ISK is. So with the cost drop, okay. Now, what are our dynamics? Amongst all the players with a beneficial deviation, we pick the one that realizes the biggest deviation. I've just argued that in a bad state, there is a player out there who, if it deviates to its best strategy, heck, even if it deviates just to S star I, strategy in its optimal, in the optimal outcome, even that deviation will realize this massive drop in cost, epsilon over k times the optimal cost. So surely that means when we pick the best player and its best deviation, its cost will drop by at least that amount. Okay. So next move, a move following a state in which this guarantee is violated. Oh, I should say, this is also, if we want to write it in terms of the potential function, because again we're going to track progress in terms of the potential function, this is lower bounded by the potential of the optimal solution. Okay. So next move decreases potential by at least, sorry, my epsilons became gammas. Whoops, times phi, times phi. Okay. So let me just wrap up. So you get this factor decrease after L iterations. Right, so again, every time we have a bad state, we multiply the current potential value by this 1 minus gamma over k factor. In the other iterations, the potential is only going down. So again, every time we have k over gamma, bad states, the potential drops by a constant factor at least, and that can only happen a log of the ratio potentials number of times. Say what?
Why not do this entire argument for the cost instead of potential? This just said if you look here, best response dynamics or cost of decreasing. Why did you need a potential?
Well, but it's not true the cost is decreasing. That's exactly the point, right? So consider an iteration in which there is no, in which your cost is good, right? So suppose you're not at a Nash equilibrium, but the cost is actually good, okay? And now you take some player and it updates its cost, it updates its strategy. Certainly its cost drops, right? But in general, when some player changes its path, it might get worse at the expense of others. So you have monotonicity in the potential function phi, which you do not have in the cost. Okay? So we're really using two things. We're using that in every bad state we get a massive drop in the potential, and in every other state we get at least some drop in the potential. So we can't undo the drop in the intervening iterations. Okay? So we multiply by 1 minus gamma over k every bad states. So every k over gamma bad states, we drop the potential by a constant factor, and again it's only going down over all of the iterations. So how many bad states can we have? K over gamma times log of the ratio. Okay. And again, so what's the point? The point is we weakened the hypothesis. We did not insist on converging to an approximate Nash equilibrium. And in general, we're not. Okay? So we might be in, say, a selfish routing game with multiple sources and multiple destinations. And it is not true that after so few iterations we'll be to an approximate Nash equilibrium. But the last theorem in this class, the point is, if you only cared about being at an equilibrium so that the objective function value would be near optimal, well, then actually, if you just focus on that goal rather than converging to equilibria, you can get much wider reach. Okay, so actually, any smooth potential game, you do just as well. It's as if you had converged to equilibrium. Okay? So sorry for going over. I'll stop there. See you next week.